All right, anybody got started with the homework? Oh, perfect.
I have a question. Is there supposed to be an image associated with the first problem? Because it just shows like a locked image.
Oh, it shows blank? Okay, thanks for letting me know. I will take a look at there. There should be an image. There are only a couple of people who have done the homework. Perfect. It's a perfect class for me because I wouldn't have started it either. Right, so the due date is next Thursday, 11 p.m. Again, if it takes a day or two, you can, the support portal is open till Saturday, 11 p.m. So if it takes a day or two for you to, do it stress-free, that's absolutely fine. Go ahead, but just don't make it a habit. I'll usually post the homework by a solution by Sunday afternoon. In case you haven't been able to submit it by Saturday and you need a couple of more hours or a day additional, let me know so that I'll delay the posting the solution. But once the solution is posted, unfortunately, I can't give you an extension after that. Right? All right. So for last class lecture, just a quick correction that I need to provide. I think Thomas, you pointed out, you asked a question, if I'm not wrong, that why the incremental mass is outside. Was it you or? No. So that was a mistake in the way I drew it. The incremental mass should be inside. It's just that the way I drew it, it looked up as if it was outside. And I misheard your question. I thought you were meaning the symbol that I was using, dm, why it was outside. So, but yeah, in the future, if there is some misunderstanding between the question you ask and the answer that I give, do not hesitate to ask it again. No matter how many times, we can keep going over and over until we both are on the same page. There is no hurry in this class. We have quite a lot of additional time, so we can go quite slow if needed. Okay? So this was just a drawing error. The second thing is when I was talking about the figure skaters, and where I said the figure skaters basically put their hands out to build up some energy, and then they collapse their hand closer to the body. The principle that's followed is conservation of angular momentum, not conservation of energy. We will get to what happens to energy in a second. But the underlying principle that governs is conservation of angular momentum. Right. So, for instance, when the arms are stretched out, it's J1, and when the arms collapse, it becomes J2. Let's say is equal to J1 by 2. Then J1 omega 1 is equal to J1 by 2 times omega 2. So omega 2 would end up being 2 times omega 1. Okay. So what would happen to the energy? So previously it was J1 omega 1 squared. Once the hands collapse, the energy becomes half J1 by 2 omega 1, 2 times omega 1 squared. Let's substituting this value. So we end up with J1 omega 1 squared, right? This becomes 4, this 2 squared becomes 4. So the energy doubled. So is there something wrong? Can energy suddenly increase? Why is angular momentum conserved? Is there an underlying law of nature or there is something more fundamental to it? You must have learned this in your first year physics course. Is there a fundamental law of nature? Conservation of angular momentum, conservation of energy, so on and so forth. How many of you say it's a fundamental law? How many of you say it's not a fundamental law? Okay, what is the underlying fundamental law then? I don't mean to put you on the spot though.
Like energy, well, I think conservation of energy is very fundamental, but it seems like it's not holding here. I'm not sure why.
Okay, so if we will take a look at this energy, conservation of energy is a law of nature, but it's not neither conservation of angular momentum, conservation of linear momentum, nor conservation of energy by themselves are fundamental laws of nature. The underlying fundamental law of nature is something basically the symmetry of our universe. It was established by a physicist called Noether's theorem. You should have learned this in your first year physics, but anybody know where she's from? I might have her pronunciation wrong. I learned this while I was in India, so the pronunciation would definitely be different from how it's pronounced here. Noether. She was a German mathematician, extremely brilliant. She has the honor of being one of the few mathematicians who during their own lifetime was recognized to be extremely brilliant. Lot of times mathematicians, once they die, they are recognized to be extremely brilliant, but she had a unique recognition during her lifetime. But she was born during the wrong time period though. In spite of her brilliance being universally well known, she had to put up with a lot of shit because first she was born a woman, and second she was born a Jewish woman in Nazi Germany back in 1918. So when she applied for professorship, she couldn't get it. So she had to work under Dilbert as without getting recognition for the work she was doing. And then 5 years later, she got professorship. And then 15 years later, she had to flee Nazi Germany because she lost the position as all Jewish people were purged from their public life. Right. So she then fled the US and then she continued to work here in the US and contribute. But she comes up with the fundamental theory of why each of these do hold. For around 300, 400 years, people knew that energy was conserved, but nobody could come up with a theory as to why that was true. Right? So here comes a fascinating, brilliant woman and comes up with a very elegant theory. It basically says that if there is symmetry where, so if you do some set of experiments and say x equal to x naught, and then I repeat the same experiment at x equal to x1, some difference in distance, the results would exactly be the same. We all know this by experience, right? If all the external forces are the same, if all the experimental setup is same, irrespective of where I do an experiment in space, the results will always end up being the same. So using Lagrangian mechanics, you can clearly show that that symmetry means there is conservation of linear momentum. Right? So linear momentum and position are what's called conjugate pairs. And if there is symmetry in linear motion, then there would be conservation of the momentum as well. So it's a very simple derivation. And the same thing can be done for angular momentum. If there is rotational motion going on, you do that in one particular angle and you do the same experiment in a different angle, you would get the same result. The same thing comes from conservation of energy, that comes from the symmetry of time. So you do an experiment today at 5 o'clock and tomorrow you do the same experiment at 5 o'clock. If everything else is exactly the same, you'll get the same result. Right? So that would then again, time and energy are the conjugate pairs. So if that is symmetric, then energy would be conserved. And she laid out the theorem, Noether's theorem, which basically proves that if fundamentally you can have systems where you have the energy, then all of these laws will be conserved, right? So the fundamental law that underlies all of these is the symmetry we find in our nature. These themselves are not the conservative law. So, so angular momentum is, so conservation of angular momentum tells that the speed must be 2 times speed when prior to collapsing the hands. Why is the energy not holding? Conservation of energy is again true. We haven't broken any laws of nature. So where is the additional energy coming from? Yep, Thomas.
Linear motion inwards.
Right. So that's a very good answer. So when the person pulls their hands inward, they are doing extraordinary amount of work to pull the hands inward. Because when you're rotating, your hands want to stay outwards. Right? It takes a lot of practice to bring that hand inwards against what the nature is trying to pull you outward. So when they pull their hands inward, they're basically burning the energy stored in their body and converting it into energy that goes into this rotational motion. All right, energy didn't come out all of a sudden from somewhere, right? It's just basically converting energy stored in your body into energy that goes into rotational motion. So when you look at the closed system of the figure skater on this side skates and then pulling their hand in outwards, the energy inside the person is also part of the closed system, right? So this is just one part of the equation. There's another part of the equation which is basically the energy of the person, which is not being added here. So if you add them all, the energy before would be the same as the energy afterward. Same as when you have two bodies going at exactly same speed, opposite direction, collapse, right? They come to a full stop because momentum in this case was positive, momentum was negative. They come to a full stop because momentum will end up being equal to 0 in an elastic collision. But what happens to the energy? Energy should be conserved too, right? It was half mv square, half mv square. When they collapse, what will happen? You'll hear sound or some kind of explosion, right? One energy got converted into another energy. Same things happen here. So you're not breaking any laws of nature, but it's just being represented in a different way. Right? Do you have any questions? Okay, so we will continue with the final example of the mechanical system that we started off last class. So again, this is the equation we are trying to model. All the terms on the right hand side. So we already looked at this system. What was the example we looked at? For Tem equal to J d omega by dt. What was the example we looked at for relationship T equal to J d omega by dt? We had a very nice example. Yep.
The IKEA fan?
That would be B omega.
Sorry. Was it the flywheel and the weight?
Perfect. Flywheel energy storage. This was our fan case. So today we're going to look at a load torque kind of example. So the elevator that we have in our Keller hall, the ECE building. Last week I looked at the capacity of the elevator, the main one that's currently not working today. It's about 2,500 pounds, and again we like to keep it in SI units. That's about 1,100 kgs, give or take. So when they design these elevators, so the way this elevator works is there's usually a motor on the ceiling, in the roof, and then this is connected to some power electronics. This would typically be an induction motor or a permanent magnet synchronous motor, okay, connected to some power electronic converter, connected to grid. Typically again, a three-phase power supply for the energy of this rating. In residential buildings, when you have elevators, this can be again a three-phase motor connected to some power electronic being powered from a single-phase power supply. But in our case, it would definitely be a three-phase power supply. Okay, so the way the companies do it. So the way the elevator manufacturer decides what weight to put on this carriage, what weight to put on this counterweight would depend on what the weight of this carriage is. For this model, that was roughly around 1,000 kgs, right? And for most elevators, the carriage weight would typically be very close to the weight of the rated capacity of the elevator as well. All right, so this rated capacity is in addition to what the carriage weighs. So if it's just 100 kgs, then just one person can get on, but it's on top of whatever this carriage weight is. The system can support another 1,100 kgs, which is what is listed on the nameplate every time you get into an elevator. So they would typically say 13 people or something like that, assuming in US the average weight is 80 kgs. The counterweight would be at the same weight as the carriage. There is a caveat to it, I'll get to in a minute. But anybody want to give me a reason as to why these two weights would want to be balanced?
Because if they're balanced, then doesn't the motor not have to do any work, basically?
Okay, fantastic. So if when the elevator is stopped, again, there's a big caveat, we'll get to it, but when the elevator is stopped, let's say this motor doesn't have to do any additional work to keep it wherever it's standing. Because this weight and this weight are exactly balanced, there's nothing the motor has to do to keep it in the state where it is. Okay? So, but the way the people design the elevator, they usually add onto this counterweight additional weight of capacity, half the capacity. So typically around 1,550 kg. And the reason for doing this is when the elevator is stopped, the motor is actually not doing any work at all. The reason being that when the elevators are stopped, there's something called parking brakes that engage, which is what holds the elevator in place, so that the motor doesn't have to do any work at all during the time period. So what the elevator manufacturer wants to try and minimize is the amount of energy this motor would consume when the average number of people given throughout a day travel. What would be the average weight that this carriage carries? That is what they want to minimize around, right? So typically they would assume if the rated capacity is 13 people, they would assume on an average number of people getting into an elevator is half of that. So that's about 550 kgs. And then they add that to the counterweight, and that's the total weight they put on the counterweight. So now if 6 people get into this elevator, then this motor would have to do very little work, because this would be 1,550 kgs, this would be 1,550 kgs plus or minus some variation in individual weights. And that is all the motor would have to move up and down, right, on an average. But if sometimes lesser people get in, it would have to do extra work, or if higher people get in, it would have to do extra work on this side or either on this side, right? Everybody clear so far? Was it not a no, yes? No?
No.
Oh, where do you have a doubt?
No, I don't have any questions, sorry.
Oh, okay. Okay, so the radius of this pulley that is here, I think was 0.7 meters or 0.75. 0.7 meters. And the rate at which this elevator is supposed to go is about 1 floor per second. And those of you who have been to Keller Hall and used this elevator know that's not the case. It usually goes like 1 floor per minute, if at all of this works. But that's what it's supposed to go at, according to the data sheet. And that comes out to 1 floor in Keller is 14 feet. One day I was bored in my lab, so I just used the inch tape to measure what the floor to ceiling height was. It comes out to 14 feet. And so the 14 feet per second, again, we like to keep it in SI units. So the velocity with which this elevator travels going upwards when it's supposed to work the way it's supposed to work, and it's going 4.6 meters per second. What is the rotational speed of this pulley? In that case, how do we find out the rotational speed? Anybody? We have the velocity, we have the radius. How do we figure out the rotational speed of the pulley? Yep.
Is it linear velocity over the radius?
Perfect. So V equal to R omega. So omega is just V by R. 4.2 divided by 0.7. It comes out to 6.09. Again, units are extremely critical. In your homework, please do not forget the units. Because it makes a big difference if it's 6.09 radians per second or rotations per minute. Right? So once we have omega, let's figure out what the force experienced by this is. So let's say the elevator is loaded fully. We want to figure out the work done when the elevator is loaded to full capacity. All right. So what is the total force experienced? What is the only force acting on the system? Yeah. Gravity. So what will be the total force experienced?
Mass times gravity,
And what will be the mass?
whatever's in the elevator, I guess.
Right? So it would end up being the differential of whatever is on the right side minus whatever is on the left side. Right? So that's the reason we put the counterweight. So we have an additional 1,100 here, 1,000 base cancel. So 550 here, 1,100 here. So the difference ends up being 550 kg. So carriage plus people minus the counterweight. So that's about 550 kg. Not about, it's 550 kg. And only force acting on this is gravity. So we're just going to use 10 meters per second squared. And that comes out to 5.5 kilonewton. How do I get the torque? So I got the force. How do I get the torque? Very simple question.
Multiply the force by the radius.
Thank you. R times F. So it should be R cross F, but in our case, the pulley force experience on the pulley at the point of contact is always perpendicular to the radius. So it's just going to be R times F. And we end up with 0.7 times 5.5 kilonewton. That comes out to 3.8 something, 0.85 kilonewton meter. Once we have the torque, how do we get the power?
Multiply it by the angular velocity.
So multiply by what velocity?
Omega.
Omega, rotational angular velocity. So tau times omega. So we have to be very careful when we use this, right? If the torque is always constant and the omega is the same, then we can use it. In an elevator system, we can assume the torque to be a constant because once people get it, they're not going to fall out, hopefully. So the way force experience is going to be the constant throughout the journey. The speed will start slow, but then increase and then come slow down again. But to make the math calculation simple, we can assume on an average, it is rotating at the speed. All right. If it is not, then we can't use this, as we saw the case where we had a weight and then we pulled it upwards. If we just directly calculated with the peak torque, then we got completely wrong results. Right? We need to integrate the torque times display angle and then figure out energy, divide that energy by the time, that gives us the average power. In this case, since all of those are assumed to be constant, we can use this formula. But again, be very careful when you use this book. 6.09, so that comes out to 24.19 kilowatt. Sometimes people like to rate their motors in HP. You can look up what the conversion for kilowatt to HP is. I think it's like 735 watt, 735 watts is 1 HP. So, or in and around there. So, if you decide what elevator you want, then from the power equation, and once you know the power and the torque, right, you can go back and figure out what motor you need for the system. And once you figure out what motor you need for the system, you can go back and figure out what kind of power converter you need for the system based on what grid voltage you get at your facility, and then you have all of these figured out. Right? Anybody have any questions? Okay. So we made a very big assumption in this whole system, all three cases. So I told you the equation that we want to model. So this is the equation I said we wanted to model. But even going back and looking at our elevator system, I just assumed, just this part of the equation alone for elevator and ignored these two. But in reality, the other two terms are also present. Because what I put here, this pulley is basically a flywheel. Right? It has sufficiently large enough radius with sufficiently big enough thickness that it becomes a nice cylinder with a lot of inertia. And then add on to this the carriage and the counterweight, which are all extremely heavy things, right? It's going to have a lot of inertia themselves. So I can't ignore the inertia term associated with the system. Right? And as this rotates, it is going to experience friction between the rope and the pulley. And it's also going to, as these carriages go up and down, as the disc rotates, it's going to experience viscous friction as it cuts through air. Right? And then these safety brakes, which are always present, keep sliding across the rails. Those again would experience friction always. So I've ignored the friction term, I've ignored the inertia term, I've just assumed it to be tau L alone, which is not always true. We need to look at, if you want the perfect response, dynamic response of how this elevator would behave, like we need to model each and every single one of those. So even looking at our fan case, where I said it is just tau equal to B times omega for the fan. But again, it's not going to hold true in reality, because when you have these industrial fans with extremely long blades, that again has huge amount of inertia, right? It's going to take a lot of effort to rotate those and build up the energy in this for it to get to some particular speed. So even in that simple case, the model should have been B omega plus J times d omega by dt, right? So let's go back to the fan case and see what would happen to the speed if I apply a step change in the load torque. Let's say this is connected to a motor, and the motor somehow generates a torque, which we'll get to the theory of it. So TEM is the torque generated by the motor that's connected. Right? So the motor torque suddenly increases. Before it was 0, at time t equal to 0, it increases by a step. Let's call this 10 Newton meter. How do I figure out what the response of the speed would be? And let's assume at time t equal to 0, the speed was initially starting at 0. What would be the response of the speed? Given a fixed J value and a fixed B value.
Would it be exponentially decreasing, or it would start off fast and then slow down?
Okay. What would be the steady state value? How do you figure out what the steady state value is?
Set d omega to 0.
What's it?
Set d omega dt to 0.
Okay. So in a DC circuit, DC network, right? This is basically saying steady state means that the variable differential terms become 0. So a lot of you who are from electrical background might find it hard to visualize the mechanical aspects of it, or at least I do. So whenever there's a mechanical equation, I always look at it as an equivalent electrical circuit. So this is same as having an expression. Again, we would like to represent torque as a current source instead of voltage source, but just for simplicity of this example, let's use the voltage source. So I'm putting instead of the torque, I'm using voltage, and then j d omega by dt, I'm replacing it with L di by dt, and then b omega, I'm replacing it by Ri, and I'm assuming torque is same as the voltage, and the speed is same as the current. Now we all know how a step response and voltage would look like for this particular circuit. Even without thinking, we can immediately figure out what these values are. So if I apply a 10 volts, let's say this is 1 millihenry, this is 1 ohm. What is going to be the steady state current once I close the switch? Amps. Okay. So that's just going to be V by R. Same thing is going to happen here. At steady state, it's going to be whatever the tau EM, which was 10 Newton meter, divided by whatever the frictional coefficient of the span comes out to be. Right? How do we solve this? Very simple expression. You can directly, it's a straight order, straight form, first order ordinary differential equation, so you can directly solve it. It's always nice to go to Laplace. So if you take the Laplace transform of that equation, over the Laplace transform, this is straightforward, b omega, what was the Laplace transform of the second term be?
J omega s.
Perfect, thank you.
Are we assuming it was at 0 when it started?
Yep, we are assuming speed is 0 when it started. Because similar to the, in this case, when the switch is open, the current is equal to 0. So we're going to assume starting at 0. Otherwise, we'd have to include the omega not omega of 0 term as well. Omega of s. So we have omega of s equal to Pem of s divided by Sj plus b. This is varying as a step, right? What is the Laplace transform of the step function?
Over us.
10 over s. So if it was just going from 0 to 1, it would have been 1 over s. Since it's going from 0 to 10, 10 over s times 1 by Sj plus b. Do you want to do partial fractions and give me the value? Yes, I know, I want to split these two into two parts. Right, so there is no j in the numerator, so I need the j to go away. So this multiplies becomes sj. So I need to have a negative j here. So that those terms cancel away. What is left would be b, but again the numerator doesn't have any b. So divide by a b. That's pretty much it. Take the inverse Laplace. So we have 10 by b times inverse Laplace of 1 by s is just 1. This would be e power minus. So let's pull out the j terms common on the numerator and the denominator. This will become b by j. So 1 by s plus alpha, inverse Laplace of that is negative alpha t, right? Where alpha is b by j. And we'd like to represent it in a different form. This we want to put it in minus t by tau, where the tau is the time constant given by k by b. Right? In case of our RL network, that would have been L by R. What is the meaning of this term time constant? What does it physically imply? In our response, what does the term tau indicate?
Is it 63.2%?
Perfect. In the back, you also had the same answer.
Yeah,
Oh, you had a different one?
well, I was just gonna say it represents how long it takes like a function to rise or fall.
Okay, perfect. So it's the time. Both of the answers are perfectly correct. So when t equal to tau, the value would have reached 53 63.2% of the final value. I think it's 63.2, or it's basically 1 minus 1 by E. In ratio, converted to percentage, whatever that comes out to. Right, so this would be I think 0.75. So it's the amount of time it takes for the current in this case, if it goes to 10 ampere, it is the amount it takes it for it to go to 6.32 ampere. There's another nice way to get an understanding of what's happening. So the other way to look at time constant is if the current was raising, so as the current over time, what happens is the current starts to, rate at which the current starts to increase, starts to come down, right? That's why it never goes to 10 ampere, it takes infinite time to get to there. But if it were rising at the same rate at which it started off, so if it rises linearly at the same rate at which it started off, the time it would reach the 10 ampere would be equal to same as the time constant, right? So that's another way of looking at it. So what that means is if you make your inertia larger or if you make your inductance larger, it is going to take a much, much longer time for the system to go close to the steady state value that we want it to go. Right? Anybody has any questions? Okay. So with that, we are mostly done with the mechanical system, at least for what we need for the course. Let's look at different kinds of loads. Can you give me an example of a load on a motor which would act independent of omega? So irrespective of what speed the load is rotating, the torque should be a constant.
I have a question on the last problem. When you're doing the tau equation, you don't have tau subscript E.
I don't
as
have
the
what?
first term. Like when you originally gave the equation for electromotive torque, I'm guessing, there's a first term that's like for both of those. Why didn't you include that?
Can you repeat this? Sorry, I'm not able to hear you.
Yeah, you're okay. So originally when you gave the equation for the electromotive torque, you gave 3 terms and you're only having 2 in that equation that you have at the top of the board. I'm wondering why we aren't considering that third term.
This one.
No,
Tau
that,
L
No.
in the,
Yeah, thank you.
tau L.
Oh, now, so in the case of the fan, oh, okay. So when we have a fan, it's a very good question. So when we have a fan, so the towel would indicate, let's say we had some kind of mechanism where somebody, so when you're a kid, you might have done this in a ceiling fan, right? You'll hold on to the ceiling fan and rotate with it. If you're doing that, you're adding additional load torque to the system. Otherwise, you're not putting any additional load torque into the system. Right? All the torque that's being experienced by the system, when the motor is rotating this, the blade is cutting through the air, which is having friction. And then this whole system itself is an inertial system. So to accelerate up, there is some amount of torque that's needed. Right? There is no additional force that's pushing on this blade in any mechanism. If you had like a broomstick or something and you're trying to tap on the blades, that would then be added as a load torque condition. Right? So we are not putting any other additional torque on the system other than what the system itself creates.
Thank you.
If the blades had a significant amount of mass, would tau L be considered?
No, if it has significant amount of mass, it will show up in the inertia term.
Okay,
So tau L would be something external of the system.
okay,
Right? You're not putting it. So if you put more mass on the soul, let's say you add extra weights to the blades, that would mean the inertia of the system increase, similar to the person stretching their hands out and holding 2 dumbbells. Right? So that's all that would change. It doesn't change the added force. So if you continuously put some broomstick and keep hitting on the blade as it rotates, that would add an increased torque. That would be same like a step torque.
okay.
Right? So every time the broom hits the blade, there would be a step in the loop torque. A train of on and off, right? Anybody else? Yep, Thomas.
This is kind of irrelevant. Where's the 4R come from?
Where?
L over R, never mind.
Oh, this is the
I didn't get
electrical
that.
circuit.
Yep, that analogy.
Yeah, so in that like bottom equation, which is omega of t.
Yeah.
Uh,
Just gonna be on the camera.
what did you write? That's 1 minus e to the what? That's alpha t times b over j.
Yeah, so this After this part you clear, right?
Yeah.
It's just 1 by s plus b by j. When you learn Laplace transform, you'll have likely learned the inverse of Laplace inverse of 1 by s plus alpha is equal to e power minus alpha t. Right?
Yeah.
So this term I'm just gonna call it as alpha.
Oh, okay.
So this would be 1 minus e power minus alpha t, where alpha is b by j. But in electrical and mechanical systems, we don't like this particular form. We would like to represent it as minus t by tau, right, as some kind of time constant, and that would then be the reverse of this. Tau itself is alpha inverse, which would be j by b. If it was electrical system we are considering, it would have been L by R. Anybody else? Any questions? Right? Okay, so can anybody give me an example of a system? You've already seen such a system where with respect to what speed the motor rotates, the torque on the motor would still be the same. What system has that behavior? What idealized system would have that behavior? An elevator, right? In the case of an elevator, what determined the torque? It was just the force times the radius of the pulley. And the force itself is not being function of the omega because force was directly proportional to the number of people getting onto the elevator. So irrespective of whether your motor decides to rotate 1000 RPM or 5000 RPM, the torque experience is always going to be R times the force. And this force itself was going to be mgh. None of it is a function of omega. Right? So in this particular system, our torque is always a constant. It is not a function of omega. Can anybody give up any other example? Something that operates on a similar principle like elevator. Elevator lifts people. If it's lifting some kind of equipment or construction material, what would you use? Forklift? Or some kind of hoist or a crane? All of those, right? Anything that's acting against gravity. So given a mass, the force is always going to be a constant when it's acting against gravity. So the torque is always a constant, irrespective of what speed your motor decides to spin it. The torque experience on the load side. So this is going to be a constant independent of the speed of rotation. What is going to be the graph of the power? How is the power graph going to look like?
Linear?
Was it
Linear?
linear? Thank you. Because P was equal to tau times omega. So if tau is a constant, tau is constant when omega increases, so tau times omega will be a linearly increasing straight line.
Does that also include like an airplane motor? I know they use engines, but like hypothetically.
I'm not sure. I don't know. I don't think so because the airplane motors would work similar to a fan mechanism, right? It's cutting through air, which is what is creating the lift that we need.
Yeah.
So that would have a different characteristic we take a look at. Yeah, it won't be a constant load function. Yeah, actually it won't because when you have a quadcopter, we do have quadcopters in our labs. When you want to rotate it faster, the power does significantly shoot up almost exponentially, quadratically, but so let's look at the second case where the torque is proportional to omega. You want to give me examples? A case where torque is proportional to omega.
And
A fan. Any other examples? A very good answer, but we'll get to why it might not be perfectly true. So in case of a fan, we wanted to idealize it to a form b omega, but that is not going to be the case because whenever you have seen a fan rotating, unless it's rotating extremely slowly, right? If it's going to rotate at some relatively faster speed where you are able to hear it pretty well, that means it's gone into turbulent flow. Right? The moment it goes into turbulent flow, tau is not equal to b omega. In those cases, it becomes b omega squared. Right? So even though I said, if we are when we are modeling a drive, we would simplify it to a form b omega, because if it was b omega squared, we can't take Laplace transform. If we can't take Laplace transform, the design becomes nonlinear control, which becomes overly complicated. We want to keep it in a linear domain. So even if the response was b omega squared, around that operating point, we'll linearize it so that we can approximate it to a linear model. But truly, tan would fall under another category, which we'll take a look at in a second. But cases where torque is proportional to omega are things that move slowly enough, like paint mixers or some kind of industrial mixers, where the liquid is being mixed together but very slowly, such that air bubbles are not created, where it becomes turbulent. Then we can model it as tau is proportional to omega, tau equal to b omega. Or also rollers and conveyors, right? When this roller is rotating, it's basically the friction of the belt that's rolling on top of it, and that friction is going to be proportional. We have all done this expression, friction is proportional to the velocity at which this object is moving across the system. So in case of those systems, again, those that are moving relatively slow enough, where you can model the friction as some kind of linear relationship, those again would have this characteristic. Right? Rollers, conveyor belts, all of those. What would be the curve for the power versus omega? If the torque versus omega is linear, what is the curve? Yep, Thomas.
Exponential,
Is it exponential?
or it's not a quadratic, or
Quadratic.
quadratic, right?
Omega square.
I think of those being
Tau
very
is
simple.
proportional to omega, power equal to tau times omega, so that will be proportional to omega square. Okay? Yep.
Is the flywheel also one of these, or is that more like the fan?
Flywheel, energy storage. So the problem with flywheel is once you get to a particular speed, right, there is no amount of torque needed to sustain that speed. So it's basically zero torque once you get to that speed. So we are looking at things that have a constant amount of load torque that's being used up. So all of these have power. So when you look at a flywheel, the power curve would look like, to get the flywheel to some particular speed, you need some power. But once it gets to that speed, the power goes to zero because you don't need any torque at all. Similar to when you have an object that's moving, to get accelerate and get it to some speed, you need some power. If there is no friction, you don't need any more additional force or power to keep it moving the way it is. Right? So it doesn't fall under any of the four categories we're looking at. So we are looking at only cases where the power is sustainably used. Flywheel comes under just as a transient condition.
Does rolling resistance for like a tire increase or decrease based on angular velocity?
Yep, it does, because of this relationship.
Okay,
So
so
the
then,
tire hits the road, right? As you keep increasing the speed, the resistance will keep increasing.
okay,
But if you're thinking for the power consumption of like a car or something, electric vehicle, that would be a bit more complicated because it's not the resistance of the tire that is too much, but the car cutting across the wind, right? That goes omega, so that goes a speed square or speed cube, right? So that would add on to this system.
okay.
Even though it's not part of the rotation system, it comes into this motor torque on a different way.
So both those things are then affecting it. So would you say an electric drive like motor for a car is the torque is proportional to omega?
It's proportional to omega if you consider the interaction of the tire and the road. It will be proportional to omega square if you consider the interaction of the wind and the car. Okay. Any questions? Yeah.
Sorry, that's omega time. The F equals,
This one?
no, not right.
Oh, that's mu times some coefficient of friction.
Okay.
Times the velocity v. Any other questions? Okay, third one. What was your name again? Sorry.
West?
West. Oh, West.
Yeah, West.
Okay. So the third case, West already gave the answer. Where torque is proportional to omega square. Right, fans, again in our course, we will linearize this so that it's easier to design control system. But otherwise, truly, if you're looking at the system, torque is proportional to omega square. The torque increases quadratically with the speed, rotational speed, and the power increases as omega cube. Right? Because power is proportional to again torque times omega, torque is proportional to omega square, and then we have omega, it's at omega cube. So the final case of sustained torque, again there are cases outside of this. So even the case where I say the torque is proportional to omega squared in a fan, that is not true at all. So the ratio is like 2.5, sometimes it could be 1.8, depending on various conditions, those exponent factor changes. But we are going to simplify it into quadratic expression. We can't analyze all possible scenarios. There is a purely empirical relationship. The fourth case of most common torque conditions, sustained torque conditions, is where the torque varies inversely as a function of rotational speed. Anybody want to give me an example for this? You all have definitely experienced this in your life. You're all students, maybe you don't vacuum your houses, but I know when I was a student, how dirty my house was. But so when you have a vacuum cleaner, if it gets stuck on a thread, it comes to a stop. Right? When there is no load, you hear it spin very fast. But the moment there is too much load, it comes to an abrupt stop. Which other equipment have you experienced that in your house? Anybody do any home improvement? A drill? Perfect. So when you have a wall drill, right, when you don't put any load torque on the wall drill, you just keep it spinning in the air, it's going to rotate very fast. But the moment the drill bit hits the wall, it slows down. And the more and more load torque you put in, more and more pressure you put in, the drill bit starts to slow and it comes to a complete stop after some power rating. So drill, your vacuum cleaner, all of those have those characteristics, particularly those that are old ones. Newer ones have the real DC motor with a drive, which can overcome some of those characteristics, but old ones which have a single phase induction motor, the cheap one, like costing $30, $40, those would very well have this characteristic. Omega was a torque. And what will be the power?
Constant.
Constant, okay. It will be a constant. Because again, power is tau times omega, proportional to, since tau is proportional, inversely proportional. So 1 by omega times omega, which is the constant. So this is the idealized curve that I have drawn here. In reality, you cannot go to infinite speeds, as you all know from your drill motor that you have, and you can't create infinite torque either. You can't have infinite amount of current. So in reality, all of these would be capped. Okay? There would be some speed it can get to, there would be some maximum torque it can get to. It's all in between. But we want to look at the ideal cases for our control system design. And then the reality, if we design a good enough controller, as we'll see, all of the other oddities that come in from real world can automatically be compensated for any issue. Right? So, anybody have any questions? We have quite a bit of time left. We can get a jump start on the next topic. Since we have time, let's look at one more case. Scenario that majority of you are not going to experience in your work life, but there was a case in 1975, I think, or 76, in Navajo. You know this coal power plant. Where they were experiencing this phenomena where their rotor starts to oscillate arbitrarily and then it breaks down. So the first time this happened, they just chalked it out to being some mechanical fault in the design and they replaced another rotor. And that itself should not have happened. So it's like a 1 in a million or 1 in a billion event that such a rotor failure could ever happen. And then they replaced it. Within a couple of weeks, it failed again. But clearly at that point, it's not something of a design failure, but it was something going on in the system that was making it fail. So what was happening in this whole power plant is, how many of you have taken the power system course? Right? So you would have seen, when you have these power system, you have these transmission line, which ends up taking some reactive power, which then drops the voltage at the terminal, right? So you want to have 220 volts at your outlet, but it would typically be like 215 or 216. And particularly when it's heavily loaded, when a lot of industries, all the loads are acting at the same time, this would drop a lot of voltage. So the terminal voltage could drop a lot. It's called a ground mode. So what transmission line designers and operators, grid operators would do is they would use compensation networks. Sometimes, most of the time in parallel, but sometimes they add these capacitors in series with the transmission line. So when the transmission line takes some inductive power, reactive power, the capacitor is going to compensate by providing the reactive power so that the terminal voltage doesn't drop as the load starts to increase. But when you have an LNC combination, that also creates what's called a
LC oscillator.
perfect tank network. LC oscillator or a tank circuit. So whenever there is a sudden step change in voltage, this LNC network would oscillate. Basically, the power from the inductor would go to the capacitor would send it back to the inductor, and would go back and forth, and they would oscillate at the frequency given by 1 by 2 pi root LC. It's natural resonant frequency. Okay, or it could be 1 by 2 pi root LC. So that is it's going to set up its own voltage at this frequency. And these components in our lab circuits would typically be very small, but in our power system, these values are very large. So this frequency would be quite large. In fact, it would be lower than the 60 hertz that the grid is operating. So it creates what's called the subharmonic resonance. And what happens is these voltages, which are at say 20 hertz or 30 hertz range, which are set up by these oscillations that are going on, they would then excite the motor in a frequency that's different than the 60 hertz grid frequency. And what that then leads to is this torque to oscillate at the same frequency. So the torque would oscillate and then the speed of the rotor would oscillate. So the speed of the rotor should be constant, right? But because of this phenomena going on in that particular case where they were compensating with this series capacitance, the rotor goes through this oscillation. And these are not trivial small rotors that we saw in our lab. These rotors are for a megawatt level coal power plant. So these would extend multiple rooms of this building, right? It could be as long as this building. So, and when these go through these kind of oscillation, they end up having fatigue and they start to break down, right? So whatever equation we saw before, there is one more component that needs to be added for rotors of these extremely long length. So far, our equation was very simple. Tau m equal to tau L plus J d omega by dt plus B times omega. But so let's consider a case of a hydroelectric power plant. This was a coal power plant, but hydroelectric is a little more easier to visualize. But the case is the same though. So in a hydroelectric power plant, those of you who have gone and seen it, there is a generator and then there is an extremely long shaft that goes across the length of the dam, right? Where the water comes out of the outlet. And they have these cup bucket kind of arrangement, depending on what kind of turbine it is, Kaplan turbine or transit turbine or whatever be it, depending on the dam height. But the mechanism is still the same. Some water goes through this, sits on the rotational element, and then flows out. The energy is converted from mechanical to electrical system and then connected to the grid. So in a coal power plant, something similar happens. Even coal power plant plants are extremely large because in a coal power plant, typically it's not a single turbine that's attached to the shaft. There are two turbines, a low speed turbine and a high speed turbine. So that whatever fumes come out, they extract some more energy out of the fumes as well. And those again typically end up having to require extremely large rotor lengths because of the multiple turbines sitting on top of them. So in the hydroelectric power plant, when the water flows, there is going to be some torque. So we have a generator. This is going to generate the electromagnetic torque. Now, previous equation, I'm just going to call it tau G, right, for the generator torque. And then the load torque, I'm going to call it tau L, the turbine torque. All right. And then the rotor that is rotating inside this motor, that is going to have its own inertia. We are going to call it Jg. And then it's going to have some friction as it rubs through the air in which the rotor and the stator are separated. And then there is ball bearing as well, which is supporting the rotor weight, which again in our low speed motors and the lab motors we can ignore. But for these high power motors, they cannot be ignored because it's like a couple of tons of weight sitting on a ball bearing that's going to create a lot of friction in the ball bearing. So all of those are included there. And again, the turbine shaft, we can have some inertia for this portion of the turbine shaft. And then friction associated as well because it's flow going through water, which is quite a viscous medium compared to air. So there's going to be quite a bit of friction on this side as well. In all cases, in the lab motor, the shaft length is extremely small. By small, I mean the length of the shaft of the rotor compared to the width of the motor itself is typically around 1:2 ratio or 1:3 ratio in the best case. But in this case, the length of the rotor, ratio of the length of the rotor to the diameter, length of the rotor shaft to the diameter of the stator could be anywhere between 5 to 20, right? So the ratio is extremely large. In those cases, one of the fundamental assumptions that we made that this rotor is extremely stiff, the stiffness coefficient is infinite, that is no longer true, right? When the material becomes extremely large and the forces become very large, there is what's called torsional torque that is created. So what that means is, think of this marker in my hand. No matter how much torque I apply on both sides, it is going to rotate at the same speed, right? One side is not going to rotate at a different speed compared to the other side because there is no twisting involved. But think of a very high power system doing the same thing. So you can think of this steel rod itself as separate elements, right? We have this marker and this cap. So if I twist it, the cap is going to twist at a different angle at a different speed compared to the side of the shaft. Okay, so that's what happens when you have very large amount of torque involved on a rotor that's extremely large. One side can rotate slightly at a different, in a transient condition, rotate at slightly different speed than what happens on the right side. So there is a twist that's created, similar to when a spring, when you pull a spring pretty much, you create a lot of displacement in the spring, right? The same thing, the rotor itself starts to behave like what a spring would behave like. So we can have one speed on the left and a different speed on the right, not at steady state, but in transient. So we can have omega g here, and this side could rotate at a different speed, omega n. So what do I mean by transient? We can have different speed, but not in steady state. So when I apply, like say, a sudden load torque on this side, this speed would spike up. So let's say it was both of these were initially at some steady state value. Right? So let red be omega g. Let blue be omega turbine. Both of these are overlapping one another, but let's say I apply a sudden torque on the motor. Somehow I created a torque spike on the generator side. So this speed is going to suddenly shoot up. And then it's going to settle down to some other new speed. For that information to pass on through this side and this side to catch up, it needn't overlap on top of each other. It can be delayed. But at steady state, they would both go to the same speed, right? So that's what I mean. In the transient condition, the speed could be different. And this is very problematic because in this transient time period, one side is being twisted different from the other side. Right? So what that means is we are going to get a displacement in the angle. So how do we model this expression? So we're going to introduce a new term. Any of you have any questions with the arrangement that we are analyzing?
So the turbine is rotating one way and then we're trying to like enact change.
No, the turbine, so the turbine and the generator is rotating in the same direction at steady state. That would be the same. The torque is opposite in direction. So this is pushing a torque into the system. This would have to be the opposite direction. Otherwise, this equation won't cancel out, right? So the LHS has to be equal to the RHS. So whatever the torque the load is generating, the generator is creating an opposite counter torque so that the equation will cancel out. If say this is also generating, so let's say you have this marker, right? You try to turn it from this side, I'll try to turn it on the other side, right? So it's not going to rotate. right? But if both of us try to rotate, push it in the same direction, it's going to keep on rotating and keep on accelerating, right? So for steady state operation, when you have low torque on one side, you need a counter torque on the generator so that it matches up, so that the speed can remain constant. If there is a difference in these two torque, right? If tau em is not same as tau L, if tau em minus tau L has some finite value, then the system is always going to keep on accelerating farther and farther, right? So this is the low torque, or basically the torque generated by the water falling on the turbine, while this is the torque being generated by the generator. It should be the counter torque. Anybody else, any other questions? Right. So we are going to analyze the shaft that we have, the interconnection between the two. Right, tau shaft on the left side, tau shaft on the right side. So you can think of it as a very linear system is far more easier to visualize. When you apply a force on this block, kind of spring connected mechanism, there's going to be an equal and opposite force experienced by this block. That's right, in steady state. So the same thing is going to happen in that system that we have for our rotational mechanics. So let's look at what the tau generator is going to be equal to J B J generator, omega generator. Now, since there are two different speed, two different everything, we need to be very careful of the terms that I use. Plus the torque experienced by the shaft. Where is the torque experienced by the shaft coming from? Basically, this the torque experienced by the turbine due to the water hitting on the turbine blades, going through the system of JT, BT, coming out in this area as the torque experienced by the shaft. After some of the torque is lost in BT and some of the torque is lost in accelerating the inertia that we have. And then whatever torque we have remaining, so similarly, if you can think of it from the generator side, generator is having some counter torque. Some of it is being dropped in the friction of the rotor rotating, and some of it is being absorbed by the inertia so that it can accelerate and go to a different speed. Whatever torque remains is the remaining torque shaft that then interacts with the right side of the turbine. So there we have right side of the turbine, turbine inertia, turbine rotational speed, turbine friction, turbine speed, plus torque, load torque. Now, what is the relationship? So we know everything on this. We know the load turbine experienced, the torque experienced by the turbine. If we know what the pressure of the water of our head is and what speed the water is coming out of, we can quite easily calculate what this torque is. This torque again we can calculate from motor generated information. All of these parameters JG, BG, JT, BT can be experimentally found out as you'll do in the class 3 weeks from now when you go to the lab. The only information that we do not have is the torque experienced by the shaft. Anybody want to take a guess what that value should be?
I just have a question.
Yeah.
Is omega t in that equation the omega m on that diagram, or is it something different?
Oh, sorry, that should be omega t. Thank you. So all the turbine parameters, I'm going to have a subscript t, and all the generator parameters, I'm going to have a subscript g for the generator parameters. Okay. Thanks for pointing that. So what is going to be the expression for shaft torque? So let's say you have a spring. So this torque, the shaft is not behaving exactly like a spring, right? Because there's a differential angle on one side compared to the other side. When you have a spring, if I extend the spring, what is the relationship between the force experienced by the spring and the displacement that the spring has gone through?
K delta X or something like that.
Perfect. Anybody know is what the fundamental law for that is? What the law is? It's not fundamental.
Stokes law.
Okay. So comes from Hooke's law, it's an empirical relationship. So as you keep extending the spring, the force experienced or the force required to extend the spring is going to be equal to some spring constant times x, and it's not always true, right? It starts off linearly and then it starts to reduce, and then at some point it will collapse, where it's the breaking limit, And this again is not perfectly true. You can extend it to some extent till the absolute critical failure. But even in this region, if you keep on doing it multiple times within the same region, there is a time after which there is fatigue involved, after which even at this point keeps moving backwards and backwards, so that the spring can fail even sooner if you keep putting the cycle again and again. Alright, so the same thing happens with the torque of the rotor shaft as well. So let me introduce two more variables. So this was omega g. So the angle on this side is going to be theta g, and the angle on this side is theta t. If I have omega g, how do I get theta g? If I give you the rotational speed of a rotor, how do I get the angle of the rotor? What was the relationship between the rotational speed and the angle? What was the relationship between velocity and distance?
Derivative of the angle equals your rotational speed.
So our omega was just d theta by dt. So basically it's just the integral of omega dt, right? So similar to the Hooke's law equation, what would be the effective torque experience? Very similar phenomena. Here also the rotor itself is acting like a spring. So if you try to twist a metal rod and you release it, it's going to come back to its original state. And in the process transfer out all the energy that you put into twisting it. Right? You basically create a spring by that mechanism, right? You take a thin element of metal and just put a lot of torsion and torsional torque to it, and it ends up creating a spring.
The K delta theta.
Okay, K delta theta. Delta G minus delta T. So now we have all the expressions that we need, and this is called the torsional stiffness coefficient. So we have all three equations. Again, since I'm from electrical background, I don't get an intuitive feel when I see mechanical equations. But the minute I convert it to electrical equation, it somehow seems very familiar. So let's try and do that. So I'm going to represent the torque as a current source. And this particularly, you can represent it as a voltage source, doesn't really matter. But as we'll see in a motor, the torque is typically proportional to the current. So let's go ahead with the convention. Let's say this current source on the left is some generator torque with the current going in this direction. And then I'm going to model that the voltage at this point be equal to the generator speed. I will first draw the diagram, then we'll see if the representation is correct. So this is equivalent to the voltage at this node. This is equivalent to the voltage at this node. This is the current source value. So tau G is equivalent to the current. And tau L is equivalent to the load current of this particular circuit that we have. So let's write down the equation for this network. So can somebody tell me what the LHS, so the current coming in must be equal to the current going out. Right? So if this is an electrical circuit, what would tau G be equal to? So what would this current be? I've given you the voltage, I've given you the resistance, what's going to be the current?
G over BG.
Right, so omega G divided by 1 by Bg, so the Bg comes to the numerator.
Yeah.
Okay, so it's V by R. This is our voltage equivalent, Vg. So this is equivalent to our current Ig. So this is equivalent to our resistance, this is equivalent to our capacitance. And this is just our inductance. And this is again equivalent to our resistance, and this is equivalent to our current. What is going to be the current through this capacitor network? The relation between the current through the capacitor and the voltage across the capacitor. Anybody? So the capacitance is Jg, dV by dt, Rv is omega g. Right? And for now, let me call this current as tau shaft. We'll look at what the expression is in a second. Tau shaft. Can somebody do the same for the RHS? So the current coming in is the same current, so tau shaft is going to be equal to, what is the current through this? Anybody who hasn't participated for this lecture 4 through 7, very quick answer and you get a point. What will be the current through this? JT. It's going to be the same as this, right? We had here, the current was this C dV by dt, so C is equivalent to Jg. dV by dt was dWg by dt. So we have Jt dWt by dt plus current through this is going to be omega t divided by 1 by dt. So that's Vt omega t plus whatever current remains. Tau. So we're just doing nodal analysis. Sum of this current equals sum of all three currents coming out of the node. And then the final current is the shaft, tau shaft. What is the relationship between the current in an inductor and the voltage across the inductor?
LDIDT.
Oh,
LDIDT.
LdIdt. So I want the other way around. Current in the inductor is a function of the voltage. Just flip it around.
Just the integral of.
So 1 by k. Right? Times integral omega g minus omega t dt. So that just comes out to k times, if I integrate omega g, it's theta g minus theta t. Right? We have all the three expressions that we had here. Right? The first equation is same as the first day, second is same as the second day, third is same as the third day. So we can model our mechanical system that we have here as an equivalent electrical network and quite easily analyze what the expressions are. Now comes the nice part. What is this network, this LC, this capacitor and inductor in parallel? You only gave me the answer.
The LC tank circuit.
LC tank circuit. So this is just a resonant network. Okay. Anytime you have a step change in the generator torque or a step change in the load torque. So let's say the gates of the dam was initially closed and then they suddenly opened, or the other way around, they were open and they suddenly closed, then the load torque changes as a step. Right? Whenever the sudden change happens, we already saw what's going to happen to an LC network. Whenever you have a sudden change in the step, in the voltage or the current, so in this case we are changing the current, so the voltage is going to oscillate. And what is our voltage in this case? The generator speed omega g. Okay, so this is what was happening in the Navajo power plant, where any kind of disturbance on the generator side was happening. There was some LC network involved and they're creating some disturbance in the circuit. That in turn propagates as disturbance in the generator current, then disturbance in the generator torque, that then creates oscillation on the rotor speed, which then puts stress on the rotor, effectively breaking them. So in our course, we are not going to be worried about this effect of torsional coefficient, but it's extremely important. Those of you who go on to work in like high power system or something, that's something you need to remember. The unfortunate few who will go and work in a power plant should remember that, but majority of you would never have to go through the process, like in an EV application or any drives that you would have in your house or industry, typically would not see the phenomenon. So we'll just stick to this equation going forward, but it's just something you need to remember. And on Wednesday's class, we will start looking at power electronic converters and look at how buck converters also
I don't know. Like I don't know. Why?
You too?
I'll meet you in class.